Hello friends, welcome to this lecture on mechanical behavior and testing of materials. So as promised in the previous lecture, what we will be doing is we will be shifting our focus to whatever we have been seeing in the previous lecture to something new now. So we will be looking into the aspects that we have so far not looked into, and we will be learning some new interesting things both theoretically and also from the application point of view. Now, to begin with, if you could recollect, all our discussion started with the graphical representation of how a material would respond to an imposed mechanical condition. So, this we represented in terms of, to begin with, when we represented in terms of load versus deformation curve. Now, if you could replace this deformation in terms of dl, it is nothing but change in the length or the longitudinal dimension of the material when you impose load onto it. So this response we plotted against the mechanical condition that we imposed, and we saw that for a crystalline material there is a representative plot which would represent or which would depict the way a material would behave under a imposed load. So this load was uniaxial tensile, and this here, the elongation or the deformation or the change in the dimension is nothing but L minus L naught. So L naught is the original length and L is at a specific time, or it is what we see for a given load, what is the dimension, and this we subtract it to the original length and we get the amount of deformation or change in the dimension that is exhibited by the material. So we largely focused our discussion on a specific region of this curve. So if you could recollect, this curve, a representative form of it would look like something like this. So our discussion so far has been confined to this region here. So whatever discussions we had, whatever properties we defined, whatever material parameters that we considered, all was confined to this region, and this deformation or this behavior of the material for the given load, we refer to it as the elastic behavior or elastic deformation. And the strain that we focused here, or the change in the longitudinal length that is confined to this region, is nothing but the elastic strain. In this lecture and moving forward, what we will be looking at is the other part of this curve or this region here. So our focus will be on this region here henceforth. Without knowing much of it, without knowing what is happening to the material or what are the mechanism that renders this behavior of the material, or why there is a change in the behavior of the material, or what exactly brings about this nature here, just by looking at it, the trend of the curve, we could say there are some specific points that characterizes this curve. So you have a representative curve and you don't know much about it, but just by looking at the curve, how the nature of it is, you could see there are some specific points. So one point, let me use another color here. So one point here is something that is important because it shows that there is a transition in the curve. So if you assume this region to be a linear region, and this part and beyond this point here, the linearity is lost, and you could say, just with respect to this variable, not in the general terms of mathematics, just with respect to this variable, this region, the subsequent region after this point, say, let's just assume it to be P1. So after this point P1, whatever behavior of the material is, it is non-linear with respect to the variables that we have considered here. So with respect to the load and the deformation, whatever region that succeeds point P1, it's a non-linear region. So that is one point that characterizes this whole curve. So there is a point beyond which the behavior of the material is non-linear with respect to load and deformation. And the other point that is significant or that is conspicuous that you can see from this curve is this point here. Let's just say P2, after which there appears to be a decrease in the load. So you have your P1, after which the linearity of the relation between load and deformation is lost, and after P2 the increase in the load begins to decrease, and finally there is point P3 wherein the whole test or the behavior of the material in response to the load is lost. And this P3 we have already seen in our initial studies, and this P3 is nothing but failure condition. So the P3, if you take the with respect to the strain here, this would be failure strain, and with respect to the stress it would be failure stress. So without knowing what is happening or what is the significance of each of these points, or what is the significance of the curve as a whole, we could see or we could distinguish the overall curve into two sections. One is the linear section and the other is the non-linear section, again with respect to load and deformation. And even in the non-linear section you have a specific point after which the increase in the load begins to decrease with respect to that of the elongation. So these are the points that you can just see or just understand by looking at the curve. So let us now try to understand what these points signify, or what is the relevance of this point to the behavior of the materials. Now, even though we began by considering load and deformation, we saw that load and deformation is specific to the dimensions of the material, and when you want to report something or report particularly the mechanical behavior of the material, if it is dependent on the dimension of the specimen that you take, it is really difficult for you to express it in an objective manner. So what we did was we normalized the load with respect to the cross-sectional area of the sample, and we called that as stress, and we normalized the deformation with respect to the original length of the sample, and we call that as strain. So this dl by L0 is nothing but L minus L0 by L0. Now this definition of stress and this definition of strain is referred to as the engineering stress and strain. So this definition of stress, wherein the load is normalized by A0, and this definition of strain where the deformation is normalized by L0, where A0 and L0 are original dimensions. So these are original dimensions, and when you normalize here load and deformation with respect to the original dimension, then what you end up having is engineering stress and engineering strain. Now if you plot your curve not based on load or load and elongation, but engineering stress versus engineering strain, the trend is going to remain the same, except the magnitude or the values in the x and y axis would vary. Now if you plot your engineering stress and your engineering strain, the trend of the curve would remain the same. You would have your linear region, you would have your non-linear region with respect to stress and strain, or engineering stress and engineering strain, with the definite points that we have seen. Now, given this trend of the curve, we can section the whole of the engineering stress versus engineering strain curve into two, and that is this region here and the other region here. So the whole of this region here and this region here. So we are sectioning the whole of the stress strain curve, that is engineering stress and engineering strain curve, into two sections. One is the linear section. This we saw as the elastic region, and this non-linear region is much different from the elastic region. So let's see or begin with understanding what is different in this region. Supposing within the elastic region, this is within the elastic region. Now what I am doing is I am loading my material or imposing a stress to my material within the elastic region, or engineering stress particularly, and I'm understanding or I'm calculating the strain exhibited by the material. After a certain point within the elastic region, this elastic region is characterized by the linear relation between the stress and strain. After a certain point, what I'm doing is I'm unloading my material. So I'm imposing a tensile load. So in case 1, I'm imposing a tensile load within the elastic region or within the elastic stress, and I'm observing some response to the material in terms of the change in the longitudinal dimension. And now after a certain point within the elastic region, I'm beginning to unload. Now what I would observe is the curve would trace its path. So if black arrow represents loading, and if I assume the red arrow to be unloading, the deformation would, if I calculate while I am unloading, or if I calculate the change in the dimension of the material or the decrease in the dimension of the material, it would follow the similar path, and ultimately I will end up with the initial state of the material. So within the elastic region, when I am loading and when I am unloading it, the path remains the same, and I got back to the place where I started. So therefore, in this elastic region, whatever changes we observe are reversible. However, when I move away from this elastic region, supposing, let us not quantify how much we move away right now, but let's just say we are moving away from the elastic region and we are considering the engineering stress and engineering strain. So what we are essentially doing is we are moving away from the elastic region by some amount, and now I begin to unload my material. So I am loading my material represented by the black arrow. Now I begin to unload my material. Then what would happen is the material or the dimension of the material begins to decrease, as you would observe in case of the test or the deformation during within the elastic region. Even in the similar case, even if you move away from the elastic zone or the elastic region of the stress strain curve, there will be, once you begin to unload, there will be a decrease in the dimension of the material, and they would follow a certain trend. However, when after sufficient amount of unloading or after complete unloading, when my load that is acting on the material or the external stress that is acting on the material is absolutely zero, there exists certain amount of strain in the material. There continues to exist certain change in the dimension of the material. So if you want to talk in terms of the longitudinal dimension, so within this elastic region, if this is the dimension of the plate at say point 1 here, and after unloading you end up with the dimension point of say point 2 here. So this would be equal to the dimension that is at the beginning or the original point 0. So that is the L0, and L2 would be equal. L0 would be equal to L2, and L1 will be of course greater than that of L2. Now in this case we have similar setup. The point 2 is here, the point 0 is here, and the point 1 is the point 1 is here, the point 2 is here, and point 0 is here. So in this case, when you move away from the elastic region, now the L0 will not be equal to L1, of course, because you have the L1 is a condition where you are applying a load, and the load you have been applying the load, and the load is continued to be imposed on the material, and at that point of course the L0 will not be equal to L1. In fact, L1 will be greater than L0. However, when I unload completely, the condition that I am imposing on the material, when after the point L1 I remove the mechanical condition that I am imposing, the load I am imposing completely, even then the dimensions of the material will not be equal to that of L0. The L2 will not be equal to that of L0. In fact, the L2 will be greater than L0. So what we observe is, so L0 is more or less at this point is the original dimension, and at this point it is L2, So there is a significant difference in the longitudinal dimension of the material, even though the material is not experiencing any load. So what essentially has happened is there has been a irreversible change that has occurred to the material. Now in the elastic region, we saw whatever change in the dimension, once you begin to unload it, it reverses and it gets back to the original dimension. But in case of once you move away from the elastic region, the material begins to change or deform irreversibly, and the dimensions that you get will not be equal to that of, even after unloading, the dimension that you end up with will not be equal to that of the original dimension. So such behavior or such deformation is referred to as the plastic deformation. So the elastic deformation or change is a reversible one, whereas the plastic is an irreversible one, or to put it in general terms, this is a permanent one. Yeah, so this is a permanent one. Now, when you talk from the view of the positions of the atom, whatever happens in the elastic region or whatever happens during the elastic deformation, the atoms assume a metastable position. So the atoms in the elastic deformation, they assume a metastable position. They don't assume a stable position, they assume a metastable position, and once you unload the material, it moves back to its original position, that is the stable position. So upon unloading, or once you remove the mechanical condition that impose on the material, the atoms will go back to their original position, and thereby you would end up having the you would recover the original dimensions that you have, or that the material initially had. However, when this happens in case of the elastic deformation. Now, in case of the plastic deformation, the atoms, they find a new stable or equilibrium position. They find a new stable position, and that is the reason why when even after unloading, you won't get back to your original dimension, but you will end up having a new dimension. So from the atomistic point of view, whatever you observe in the elastic region, it is reversible because atoms occupy a metastable position, and once you unload it, it gets back to its original position. However, in case of plastic deformation, or when you go beyond the elastic regime, the atoms would find a new position, and therefore even after unloading, you will not be able to regain or recover your original dimension, because now the system has reached a new equilibrium state, and atoms, they have occupied a new stable positions. Now this point here, which indicates the shift from the elastic region to the inelastic or the plastic region, is referred as the proportionality limit. So what we have is, we have a stress strain curve, and beyond a point, the linearity between the engineering stress and the engineering strain is lost, and this point wherein the linearity is lost is called the proportionality limit. So proportionality limit is a point wherein below it there is a linear relationship between the engineering stress and engineering strain, and above it there is not a linear relationship, so it is not linearly proportional, and that is what we mean by proportionality point. So this proportionality point, even though it talks about the linearity, if you talk about the in terms of the deformation of the material, below the proportionality point it is elastic deformation, and above the proportionality point it is plastic deformation. So this proportionality point it can also be referred to as the elastic limit. So the point beyond which the linearity is lost, we refer to it as the proportionality point or the proportionality limit. And since below the proportionality limit we have the elastic region, and above the proportionality limit we have the plastic region, this proportionality point also differentiate the elastic limits and the plastic limit. So the proportionality limit can be related to, or the proportionality point can be related to the elastic limit as well. That is, if I refer to this as P, then any stress that is below P will be within the elastic limit. So if there is a specific description or a designation for the elastic limit, say if this represents, this particular stress represents the elastic limit, then this elastic limit is nothing but, or it is equivalent to that of the proportionality limit, wherein you observe the deviation from the linear relationship between the engineering stress and the engineering strain. So both elastic limit and the proportionality limit, they both coincide and they both mean the same. One talks exclusively in terms of the nature of the curve, the proportionality point or the proportionality limit. It talks exclusively based on the nature of the curve, whereas the elastic limit, it talks in terms of the behavior of the material. So beyond the elastic limit you would have a permanent irreversible deformation of the material, and below it you would have a reversible deformation of the material. However, in terms, or if you talk about, or if you want to define the proportionality limit, it will be based on the relationship, the linear relationship between the two variables, that is engineering stress and the engineering strain. Now this proportionality limit or that of the elastic limit, these are something that depends on the sensitivity, or how sensitive is your instrument, or how sensitive is your testing machine. So when you want to calculate or plot the engineering stress versus strain curve, you would have a controlled variable and a variable that evolves with the material. So when you want to plot or arrive at a curve like this, an engineering stress and an engineering strain curve, you want to arrive at a curve like this, then this particular point, in order to calculate this particular point, the exact point or the proportionality limit wherein there is a deviation from, or the material begins to behave in a manner that reflects the non-linear relationship between the stress and the strain, it all depends on the sensitivity of the material. How sensitive is your testing machine? Based on that, you will be able to find the exact point of this deviation, or this point that we called as the proportionality limit or the elastic limit. Now how a testing machine works, based on that, or what are the parameters that are involved, or what are the apparatus that are involved in the testing machine, one would be able to understand the sensitivity of our test. So whenever you want to talk about a testing machine, particularly a tensile testing machine, the way we would talk about it is we consider a controlled variable which we change, and we study the response of the material with respect to this control variable. So whenever you want to talk about, or whenever a discussion is made on the, not the behavior of the material but the tensile testing machine, we select a variable that we change in the machine and we see how the material would respond to that variable. So usually that variable is the engineering strain. So in usual cases, or in most cases, the controlled variable is the engineering strain. So what this engineering strain does is, or how we use the engineering strain as a control variable, is that we keep on changing the amount of strain that we can introduce on the material, and based on the strain we calculate how much of the load is required to bring about this change. So as opposed to the theoretical study wherein so far we have been considering that the condition that we impose is the stress and the response of the material is strain. In actual tensile testing machine, what we do is we change the strain and we see how much of a load or how much stress is required in order to bring about this change, and that we plot, or that we consider in the y-axis, and we plot this curve. So for this amount of strain, for example for the strain E1, epsilon E1, how much of a stress is required to bring about this strain, we calculate, and the stress would be something like this. It would be sigma E1, and then we arrive at this point here. So we similarly do for epsilon E2, and we arrive at the point that is sigma E2 here. So all these points, on by cumulatively collecting all these points, we will be able to arrive at this curve. And here it is important for us to note that the controlled variable is the strain. However, there are also machines wherein the controlled variable is stress, but the conventional one, the largely used one, is strain. Now there is a reason why it is conventionally used, and I'll let you think about it, why strain is preferred over stress as the controlled variable, and why we would prefer controlling the strain instead of stress. I would let you get to an answer, and maybe during our next discussion class you can share it with me, or you can individually bring me your answers. Now there is a specific reason. You can argue it based on the nature of the curve. That is one of the that is a hint that I can give to you. So based on the nature of the curve, you could argue this is the reason why we are choosing strain as the controlled variable as opposed to stress. So this is how the underpinnings of the tensile testing machine is. So the tensile testing machine, it operates by considering one of the variable as the control variable, and that control variable is the strain. So for the given amount of strain, how much of the stress is required is what we get, and based on that we plot our stress strain curve. Now when we were considering the proportionality limit, so based on the amount of strain, the limit or the small amount of strain that we are able to introduce to the material, based on that we can specifically or more accurately calculate this point here. Meaning, if you are able to introduce a very small amount of strain, so say for instance there are two machines that can introduce, say, D engineering strain 1 and G engineering strain 2. So this strain here is introduced by machine 1, and this strain here is introduced by the machine 2. So this is the minimum limit that a machine or a tensile testing machine can introduce. So D epsilon E1 and D epsilon E2. So the machine 1, the minimum strain that the machine 1 can introduce is this, and the minimum strain the machine 2 can introduce is this. When the minimum strain introduced by the machine 1 is less than that of the minimum strain introduced by the machine 2, then this machine here would give you a more accurate prediction of the proportionality limit or the elastic limit when compared to the machine 2. So therefore the proportionality limit or the elastic limit, they depend on sensitivity of the testing machine. So whatever values we get that shows the deviation from the elastic point or the deviation from the elastic deformation or the linear relationship between the stress and the strain relation, whatever point we want to get or this point we want to calculate, it depends on the sensitivity of the testing machine. So such dependence is not usually accepted for our discussion. So that is the reason why we changed the load to stress and deformation to strain. We don't want to have any external influence on either the behavior of the material or the response of the material, let alone the property of the material. So this point here, you can think if this is a question for you, is it a property of the material or a behavior of the material? So you can think and argue among yourself, but it is difficult for us to express either behavior or the property of a material that is dependent on an external agency. We don't want to have any external factors controlling the values that we get for the specific either behavior or the property of the material. So if you think that this is the property of the material, then supposing two testing machines gives you two different values, then it won't be acceptable to us. So in order to calculate the point, or in order to define a point that shows that gives an unified value beyond which whatever happens is predominantly plastic in nature, we have another point defined for it. So even though we can use the proportionality limit or the elastic limit to describe a point beyond which there is an onset of plastic deformation, there is a beginning of plastic deformation, this point is dependent on the sensitivity of the testing machine. So we cannot use it as it is. So therefore we defined another value that is similar to that of the proportionality limit, which states that above this limit or above this point in the curve, whatever deformation happens is permanent, whatever elongation happens is permanent. So that point is referred to as the yield stress. So given that the proportionality or the elastic limit is dependent on the sensitivity of the machine, now we introduce a new point or a new parameter called the yield stress, which defines whatever the proportionality limit as or the elastic limit as defined. It states that beyond this point in the curve, whatever deformation the material exhibits, there is an irreversible component to it. Now whatever change beyond this point happens to the material, it is irreversible nature, there is a permanent damage that is done to the material. Now this yield point or the yield stress is calculated by considering a definite value of strain. Now the stress strain curve, the yield stress is calculated by considering a definite value of sign. So this is your engineering stress strain curve, and this point is the proportionality limit or the elastic limit, and this point is largely a theoretical one because it depends on the sensitivity of the material, and therefore we need a different point, and for that we want to refer to, or we want to calculate the, or we want to have a parameter that will show you irrespective of the material or irrespective of your testing machine. From this point onwards, there will be a permanent damage that will be incurring in the material, and that point we refer to as the yield stress, and we calculate the yield stress by considering a definite amount of strain. We consider initially a definite amount of strain, and from that point onwards, say if I assume a definite amount of strain, that is epsilon E, say we are talking about yield stress, so let us have y, epsilon E y, and from that point I draw a straight line that is parallel to that of the elastic region here. So a straight line that has the same slope as the elastic curve here. So I draw a straight line, and we know what the slope here is. Again, you can recollect your understanding of the stress strain curve in the elastic region. We know what this slope here is, and with respect, or by considering the same slope from the point here, we draw a straight line, and the point where this straight line intersects the engineering stress strain curve is referred to as the yield stress. So what we are defining is, we are defining a point beyond which whatever changes the material exhibits, there is a permanent component or irreversible component to it, and in order to define such a point which is irrespective of the sensitivity of the testing machine, we consider a definite strain that is here, and from that point that represents the definite strain, we draw a straight line which is parallel to that of the linear region or the linear line in the elastic region, and the slope of which is also equal to that in the elastic region, and this line intersects the stress strain curve at a point, and that point, the stress at that point, is referred to as the yield stress. So generally, by convention, the strain considered here is generally 0.2% or just 0.2. So the strain considered here is 0.2, or we can also write it in terms of percent. So 0.2%, and The straight line is again drawn from this particular point here, where the slope of the line is equal to that of the slope exhibited by the curve in the elastic region. And based on this line here, or based on the intersection of this line on the stress strain curve, we arrive at a specific point that we refer to as the yield stress, and beyond the yield stress, whatever deformation the material exhibits, there is a plastic component or an irreversible component to it. The yield stress calculated by this value or by this approach is referred to as the offset yield stress. So the point that we call as the yield stress, when we calculate it using a definite amount of strain or a specific amount of strain, this approach of calculating the yield stress and the value that we get is referred to as the offset yield stress, and the specific amount of strain that we have considered is the offset value. So the specific amount of strain is the offset value, and the stress that we get from this offset value is the offset yield stress, and beyond this yield stress, whatever deformations we have is the plastic deformation. Now let us consider a system wherein you have loaded the material beyond its yield stress. Now beyond the offset yield stress, you have loaded the material and you want to calculate the amount of permanent deformation the material has exhibited or that has occurred in the material without unloading it. Now you have your stress strain curve, you have loaded your material beyond the yield stress, or beyond, of course, when you talk about the yield stress, it is of course beyond the elastic or the proportionality limit. So beyond the yield stress, you have loaded your material and you want to know how much the material has deformed plastically or irreversibly without unloading it. So this is the engineering stress, and this is the engineering strain, and this is the nature of the plot, and you have loaded up to this point. Now here somewhere is your yield stress and here is your proportionality point, and now what you want to know is how much of the plastic strain or how much of a permanent deformation has occurred in this material. Now to understand this, we have to think about how the material behaved when we unloaded the sample. So we already saw when we unloaded the sample within the elastic region, it retraces its paths, but when the material has deformed irreversibly, then the path it retraces is similar to that of the elastic region, meaning it follows a slope that is similar to that of the elastic region. As you can see here, when you unload it after a permanent deformation, the path it follows is similar to that of the elastic region in the sense that the slope remains the same and it is parallel to that of the elastic region. And the point where such, or when this unloading occurs, or the deformation that is corresponding to the unloading behavior or unloading condition occurs, it ends up with the permanent deformation here. So this is how we saw a material would behave under and both loading and an unloading condition. When you load it, it exhibits a permanent a combination of reversible and a permanent deformation. And when you begin to unload it, all the reversible deformation vanishes off, and ultimately you will end up with a permanent deformation. Now what is critical here is the path that it takes while you are unloading. The path that it takes is critical because it follows a path for which the slope is similar to that of the elastic region. So whenever you unload a permanently deformed material, the path that it takes is similar to that of the deformation in the elastic region, meaning the slope would remain the same, and this slope or this line with the slope where it meets the x-axis would be the description of the amount of plastic deformation. So this is how a material would behave. Now we have a condition wherein we are not unloading, but we are continuing to hold the material at a stress beyond its yield stress. Now at this point we want to calculate the permanent strain of this material. You want to calculate how much of the plastic strain this material, or how much of a plastic strain is present in this material. So for that, by considering our understanding of how a material would respond when we begin to unload it, we can now plot a straight line from this point here. The slope of this line should be equal to that of the slope of this curve. So the elastic region, wherein there is a linear relationship between the engineering strain and the engineering stress. So this linear relationship, it follows a definite slope, and what we are doing it is based on the slope we are plotting a line from the point here, and this line intersects or meets the x-axis, that is the engineering strain at say point epsilon EP, and this strain here is nothing but the plastic strain. So based on the understanding of how a material would behave when you begin to unload, the mechanical condition that you have imposed in order to bring about a plastic deformation. So based on that understanding, you can calculate any plastic deformation alone. So plastic deformation exclusively can be calculated any point within the stress strain curve. So if you have a stress strain curve, any point within the curve, you will be able to calculate the plastic deformation alone by considering a line that is parallel to the elastic region, meaning the slope of this line that we consider in order to calculate the plastic strain should be equal to that of the slope that we consider, or that is observed in the linear region between the stress and strain curve. If the slope here, if we refer to that as E, and then the line that you plot in order to calculate the plastic deformation exhibited by the material at this point should also be E, and when you draw a line from that point of the slope E parallel to this elastic relation or the linear relation, then you would end up with a definite plastic strain, and that plastic strain is what is present in the material. Even without unloading it, you would be able to observe that plastic, or you will be able to calculate that amount of plastic deformation or that plastic deformation. And of course, even when you unload it, you would see that this the material would retrace, the behavior of the material would retrace the line that we considered for calculating the permanent strain within the material. So for this load here, even if you begin to unload the material, the behavior of the material would trace the path that we have considered to calculate the amount of plastic strain within the material. So what we have seen so far is, we have seen a proportionality limit or a limit beyond which there is a change in the relationship between the stress and strain. So whatever we have seen in this lecture is, we have seen there is a proportionality limit beyond which the linear relationship between the stress and strain is lost. So that is also equivalent to that of the elastic limit. And this elastic limit or the proportionality limit is dependent on the sensitivity of the testing machine. So for that we need to introduce a new term to calculate absolutely what is the point beyond which the whatever behavior we see is plastic, or whatever behavior we see is rather it comprises of a permanent change to the material. So we need to have a definite point that describes that, and this point should not be dependent on the sensitivity of the testing machine. For that we introduced an approach by using offset strain, and this offset strain can be of any value, but conventionally it is chosen to be 0.2% of the overall strain. Then based on this offset strain, we were able to plot a straight line which has a slope that is equivalent to the slope that we observe in the elastic region, and the point where this straight line from the offset strain reaches or meets the curve, we call that as the yield stress, and because we use this approach, we call that as the offset yield stress. So whatever proportionality limit or elastic limit tells you theoretically, offset yield stress or just yield stress will give you the same information practically. So when people want to talk about a point beyond which the material would behave plastically, or you would begin to observe permanent deformation to the material, they wouldn't generally talk in terms of proportionality limit, but they would talk in terms of the yield stress. Now we also saw that when we load and unload a material beyond or within the elastic limit, the loading and unloading follows the same path, and it is important to note that path, or once you unload the material, the path it retraces will rather be instantaneous, and beyond the elastic region there is a different path that a material, or beyond the elastic limit there is a different path the material takes when you begin to unload it. And even though there is a resemblance between the path that it takes and the elastic region, because of the permanent damage or the permanent deformation that has incurred in the material, now there is a change in the dimension of the material, and that we have seen here in the loading and unloading path. So you have a permanent change in the initial or the longitudinal dimension of the material. So based on this understanding, the path the material takes when you begin to unload it after you have imposed a plastic deformation, based on this understanding we can calculate any amount of the plastic deformation. We can decouple the plastic deformation from the elastic deformation and calculate what amount of plastic strain is introduced in the material for a given amount of stress beyond the yield stress by plotting a straight line which has a slope equal to that of the slope that you observe in the elastic region by plotting a straight line. So the slope of these two lines will be equal and they will be parallel to each other, and this line, the point where this line meets with the x-axis, is the amount of plastic strain that is observed by the that is present in the material when you impose a load such as this, that is beyond the yield stress. So from the next lecture we will be seeing other characteristic points within the stress strain curve, and whatever stress strain curve that we have been talking about, it is important to note that it is referred to as the engineering stress and engineering strain, and that is the reason why we have subscript E here, and that is the reason why for all the parameters within the subscript we have included within this engineering stress strain curve we have included the subscript E. So the discussion so far has been confined to the engineering stress strain curve, and whatever we have talked about is with respect to the curve, and with respect, we have just considered 1 or 2 points with respect to this curve. So in the subsequent lecture we will see what are the other points that we have already, or that characterizes this curve, and we also see what are the other different ways to represent the mechanical behavior or the response of a material to an imposed mechanical condition, and what is the need for going for a different way of representing the stress strain curve instead of this or the engineering stress strain curve that we have seen so far. So let us continue our discussion from where we left off here.